a specific case, n distinct eigenvalues, but more generally, if it has n linearly independent eigenvectors. And the thing is, if the first one is true, it's going to imply the second. Then what we can say is A is diagonalizable. And so the decomposition that A will have in this case is P, D, P inverse. So P is some invertible matrix. D is a diagonal matrix. And the diagonal of D contains all the eigenvalues. And the columns of P are the eigenvectors of A. We can also say that the rows of P inverse are the eigenvectors of A transpose. Now, this is a much more useful decomposition if we could get it, because then we have both the eigenvalues and eigenvectors of A. Now, if A is a normal matrix, this is a sure decomposition. You have the added bonus that the columns of P are orthogonal. And then these are Hermitian transposes of each other. Okay. We'll be done before. So, if you could come up with a sequence of similarity transformations applied to A that will reduce it to diagonal form, that would be great, because then you have the eigenvalues and eigenvectors as well as the eigenvalues. Here's a problem, though. In this case of A being diagonalizable, your similarity transformations are not necessarily from orthogonal matrices. So you're applying a matrix P on one side and its inverse on the other. The inverse is no longer a transpose. You actually have to figure out the inverse. And that's something that can be quite a pain. So we prefer to use orthogonal similarity transformations to get the sure decomposition. One, because there's no inversion task. It's done for you. It's just a transpose. And the other reason is orthogonal transformations are more numerically stable. Because P is an invertible matrix, but it could be highly ill-conditioned. And then you have a big problem there. Okay. So this kind of decomposition, while lovely to get, is not always so practical to try to compute. And methods of getting eigenvectors, if you want all the eigenvectors, either compute, either you do a sure decomposition and then post-process it. That's what's usually done. Or there's other iterations that I'll show you later that can get selected eigenvectors. Okay. Now, so here's a problem. Another problem is, if you have a general matrix A, you can check if it's normal without too much trouble. But suppose it's not. You have no idea whether it's diagonalizable at all or not. So the big problem is, with this kind of decomposition, is the existence question. Not every matrix is diagonalizable at all. So that's one reason why it's not a common practice to try to compute this decomposition. You don't know if it exists. You may not be able to get it. So, if a matrix is not diagonalizable, what is the next best thing? Now, I've already mentioned that if all the eigenvalues are distinct, then you know the matrix is diagonalizable. So the problem occurs if any eigenvalues repeat. Is the matrix diagonalizable in that case? Unfortunately, we don't know. It just depends. It may or may not be diagonalizable if you have repeated eigenvalues. So in order to discuss repeated eigenvalues, here's some terminology we need. Okay, so if I have some eigenvalue, ith eigenvalue of A. Every eigenvalue has actually two multiplicities. So I'm going to use m sub I to refer to the algebraic multiplicity of this eigenvalue lambda I. And by algebraic I mean, is this the number of times that lambda I is a root of the characteristic polynomial. So if you were to factor the characteristic polynomial, you'd have lambda minus lambda I raised to some power. This is that power. All right. The other multiplicity, which I'll call gi, is the geometric multiplicity. Of the eigenvalue. And what that refers to is the number of linearly independent eigenvectors that this eigenvalue has. This marker is starting to die. Now, what do we know about, so some simple relations between the algebraic and geometric multiplicity is that the geometric multiplicity is always greater than or equal to 1 because every eigenvalue has at least one eigenvector that goes with it, and is less than or equal to the algebraic multiplicity. Now, if the geometric equals the algebraic multiplicity for all eigenvalues, so what that means is you have as many linearly independent eigenvectors as possible, then we can say that A is diagonalizable. So that's the case we prefer to have. On the other hand, if the geometric multiplicity is strictly less than the algebraic for any eigenvalue, then we say that the eigenvalue is defective. So, in other words, you're missing, it's like you're missing eigenvectors. You cannot come up with n linearly independent eigenvectors that will span the whole space. How do you fill in the missing dimensions? You have what are called generalized eigenvectors. And I'll define those momentarily.